Welcome to this lecture on Python Essentials. Today, we'll be focusing on variables, names, and expressions, which are the fundamental building blocks of Python programming. These concepts may seem basic, but they underpin everything you will write in Python, from simple scripts to large applications. By the end of this section, you should understand how variables are used to store values, how assignments work, and how identifiers give meaning to the data in your code. You'll also learn about objects and name binding, numeric types, arithmetic expressions, and style guidelines that help keep your programs consistent and readable. This knowledge will set a strong foundation for building more complex programs as we progress further into Python. Python Essentials: Variables, Names, and Expressions by the Programming Professor. In this lecture, we'll follow a structured outline that begins with variables and assignments, the most basic way to store information in a program. From there, we'll move into identifiers and naming rules, learning how to properly choose and use variable names. We'll then cover objects and name binding, where Python handles data behind the scenes, followed by numeric types, including integers and floating-point numbers. Arithmetic expressions and operator precedence will help us understand how calculations are carried out, while Python-specific expressions and compound operators add efficiency. We'll also look at division and modulo, importing modules like the math library, and using random numbers. Finally, we'll explore text handling through Unicode and escape sequences, and wrap up with Python style guidelines. Let's start with variables and assignments. In Python, a variable is essentially a name that refers to a value. Assigning a value to a variable is done with the equal sign, which in Python doesn't mean mathematical equality, but instead means binding a value to a name. The left side of an assignment must always be a variable, and the right side can be a literal, another variable, or an expression. For example, assigning 5 to a variable x, then setting y equal to x and z equal to x plus 2 demonstrates how assignments build on each other. The variable always holds the most recent value assigned to it until that value is replaced. This is one of the most common operations in programming and is critical to how programs process data step by step. Sometimes, variables appear on both sides of an assignment statement. For instance, writing x equals x plus 1 is a way to update the value stored in x by adding 1 to its current value. If x started with 6, this statement would replace it with 7. This is called incrementing, and it's a very common programming pattern. The important thing to remember is that in Python, the equal sign is not equality, as in mathematics. It's an action that assigns the result on the right-hand side into the variable on the left. This means the old value is overwritten, and only the newest value is kept. Thinking about variables as boxes holding values can help. Each assignment simply puts a new item into the box, replacing whatever was there before. When naming those boxes, or identifiers, there are important rules and conventions to follow. Identifiers must start with a letter or an underscore, and can include letters, digits, and underscores after that. Python is case-sensitive, so capital cat and lowercase cat are two different identifiers. While you technically can use names that start and end with double underscores, like init, these are reserved for Python's internal uses and should generally be avoided. Instead, good identifiers should be descriptive and meaningful, such as temperature or user age, rather than short or cryptic labels. Some names are completely off-limits because they are reserved keywords in the language, like and or true. These words already have special meaning to Python. Using clear, valid identifiers makes code much easier to read and understand for both you and anyone else working with your program. When writing identifiers, it's not enough to simply follow the basic rules. We also need to follow style guidelines that make code consistent and professional. Python's community encourages conventions documented in PEP 8, the Python Enhancement Proposal for Style. For variable and function names, this means using all lowercase letters with words separated by underscores, a style called snake case. The goal is clarity. A name like temperature Celsius is far more informative than a single letter like T. In scientific or engineering contexts, appending units to variable names can be especially helpful. Abbreviations should only be used if they are very common, such as TV model. At the same time, names should not be so long that they clutter the code. Striking a balance between descriptive and concise is a skill you'll refine as you program more. Building on this, let's look at meaningful names and reserved keywords. A meaningful name clearly indicates what the variable represents. For example, if you are storing the number of students attending a class, calling the variable num students is far better than just ns or num. Similarly, for the size of a TV, a descriptive name like diagonal TV size inches tells you exactly what the number means. Using vague names like P or guess leaves the purpose unclear and confusing later on. Python also reserves certain words that cannot be used as identifiers because they are part of the language syntax. Words like if, while, return, or class already have predefined meanings. Accidentally trying to use them as variable names will result in errors. Keeping identifiers meaningful and respecting reserved keywords makes code both correct and easy to read. Now let's talk about objects in Python. Every value you create in Python, whether it's a number, a string, or even a list, is represented internally as an object. You don't have to manually create these objects. Python does this automatically when you assign values. This means that when you write equals 4, Python creates an integer object with the value 4 and assigns it to the variable name. The same happens with strings or lists. A critical idea is that everything in Python is an object, and each object has 3 essential properties: its value, its type, and its identity. The value is the data it holds, the type defines what operations it supports, and the identity is its unique location in memory. Understanding objects lays the groundwork for exploring how Python manages memory and executes code. Expanding on objects, we need to understand name binding and garbage collection. When Python evaluates something like 2 plus 2, it creates a new object with the value 4. If you don't assign that value to a variable, it may be used temporarily and then discarded once it's no longer needed. This process, where Python automatically frees memory, is called garbage collection. Name binding occurs when a variable is assigned to an object. You can bind multiple variable names to the same object, but each name always points to exactly one object at a time. For example, if you set equal to 4 and then assign y equal to x, both variables point to the same object, the integer 4. When Python sees that no variable names refer to an object anymore, it automatically deletes it to keep memory efficient. Another important property of objects is their type, which determines what you can do with them. For instance, integers can be added, multiplied, or divided, while strings can be concatenated and repeated. Once an object is created, its type never changes. You can check the type of any object in Python by using the built-in type function. Alongside type, mutability is also significant. Immutable objects like integers and strings cannot be changed once they are created. Reassigning them simply makes a new object. Mutable objects like lists or dictionaries can be modified in place without creating a new object. Recognizing the difference between mutable and immutable types is crucial for writing efficient programs, because it affects how variables behave when passed around or updated within functions. Every object in Python also has a unique identity, which distinguishes it from all others. You can think of identity as being similar to an address in memory, though Python doesn't expose the actual memory details directly. Instead, you can use the built-in ID function to see the identifier associated with an object. Even if two objects have the same value, they may not share the same identity because Python could store them separately in memory. For example, creating an integer object with the value 4 and a string object with the text ABC produces different identities, even though both exist at the same time. Only one object at a time may have a given identity, so this property helps ensure that Python always knows exactly which object you are referring to when you work with variables or perform assignments. Now let's shift to numeric types, starting with floating point numbers and scientific notation. A floating point number represents real numbers with a decimal point, such as 98.6, 0.0001, or negative values like negative 666.667. The floating in floating point refers to the fact that the decimal point can appear anywhere, essentially floating across the digits. In Python, floats are their own type and are especially useful for representing measurements or values with fractional parts. Even when the fractional part is 0, as in 1.0 or 99.0, the number is still treated as a float. Scientific notation is also supported, allowing very large or very small numbers to be expressed compactly. For instance, 6.02 E23 means 6.02 times 10 to the power of 23, while 1.0 E-3 means 0.001. This notation is critical in scientific and engineering applications. To see floats in action, consider a simple program that reads a distance in miles and calculates travel time by plane or by car. Since user input is initially read as text, the program uses the float function to convert that input into a numeric value. Once the value is available as a float, you can divide it by speed values to determine how long travel will take. In the example shown, dividing miles by 500.0 estimates flight time, while dividing miles by 60.0 estimates driving time. Using floating point ensures that fractional results, like 0.9 hours to fly or 7.5 hours to drive, are represented correctly. The program also demonstrates how Python's print function handles floats naturally, displaying decimal results without extra effort. This makes floats an essential part of programs that work with real-world, measured data. While floats are flexible, they also have limits. Python represents floats according to IEEE 754 standards, which means values must fall within a specific range. For example, the maximum float value in standard Python is about 1.8 times 10 to the power of 308, and the smallest positive value is around 2.3 times 10 to the negative 308. If you try to represent a number larger than this, Python raises an overflow error. Overflow occurs when a number is simply too large to be stored in memory. To demonstrate, raising 2.0 to the power of 256 or even 512 works fine, but raising it to 1024 causes an overflow. For this reason, floats are best used to represent measured quantities like distances or weights, while integers are better for counted values, such as numbers of people, cars, or days, which don't require decimals. Another important aspect of floats is controlling how they are displayed. Many floats, especially irrational numbers like pi or repeating decimals like 4.3333, have infinitely many digits. By default, Python displays around 15 to 16 digits, which is more precision than most applications need. To keep output readable, you can format floats to show a fixed number of digits after the decimal point. This is often used for currency, where 2 decimal places are enough, or for scientific data, where 3 or 4 decimals may suffice. Python makes this easy using formatted string literals, often called f-strings. By including formatting instructions, such as .2f, you can round the display to 2 decimal places while still keeping the actual value in memory unchanged. This is important because formatting affects how values are shown, not how they are stored. Arithmetic expressions form the core of many Python programs. An expression is a combination of items, such as variables, literals, operators, and parentheses, that evaluates to a value. For example, 2 times the sum of x plus 1 will compute differently depending on the value stored in x. Expressions are commonly placed on the right-hand side of assignment statements, so when we say y equals 2 times the sum of x plus 1, Python first evaluates the expression and then assigns the result to y. Literals, like the number 2 or the string hello, are specific values written directly in the code. Operators such as plus, minus, multiplication, division, or exponentiation tell Python what operation to perform. Understanding how to combine these components is essential because nearly every program relies on expressions to calculate, manipulate, and produce meaningful results. Once you know how to write arithmetic expressions, it's important to understand how Python evaluates them. Every expression is reduced to a value, and Python follows a strict order of operations known as precedence rules. Just like in math, parentheses are evaluated first, followed by exponentiation, then unary minus, which represents negation. Multiplication, division, and modulo come next, followed by addition and subtraction. When operators share the same precedence level, Python evaluates them from left to right. For example, if x equals 5, then x plus 1 evaluates to 6, y equals 2 times x plus 3 evaluates to 16, and x squared plus 1 evaluates to 26. By mastering precedence, you can write expressions confidently and ensure Python interprets them the way you intend, minimizing unexpected results. Sometimes, programmers run into errors by forgetting or misplacing parentheses. For instance, if x equals 3, writing 5 times x plus 1 might look like 5 times the sum of x plus 1, which would be 20. But Python actually evaluates it as 5 times x, then adds 1, giving 16 instead. This highlights why parentheses are so important. Good practice is to use them whenever the order of operations might not be immediately clear. Parentheses improve readability and reduce mistakes. A real-world example is a calorie expenditure formula, which combines age, weight, heart rate, and time into a long expression. Without parentheses, it would be difficult to follow or might even evaluate incorrectly. By grouping terms explicitly, you make both your intention and your code crystal clear to Python and to others reading it. Arithmetic expressions are not just abstract math, they show up in practical problems. Consider calculating the total cost of leasing a car. The program prompts for a down payment, monthly payment, and number of months. Each input is read as an integer, and Python multiplies the monthly payment by the number of months, then adds the down payment to compute the total cost. The final amount is printed in a nicely formatted output, showing the total in dollars and cents. This example demonstrates how arithmetic expressions combine variables, operators, and user input to produce useful results. It also shows how Python's ability to evaluate expressions inside assignments makes programs efficient and easy to follow. Even simple financial problems like this reveal the importance of arithmetic in real-world applications. Style guidelines also play a big role in making code readable, and one of the simplest rules involves spacing around operators. Python programmers should use a single space before and after binary operators like plus, minus, multiplication, and division. For example, writing numitems plus 2 with spaces improves readability compared to numitems plus 2. The exception to this rule is the unary minus used to indicate negative values, which should not include a space. So writing x-coordinate equals negative y-coordinate is correct without extra spacing. Following these conventions doesn't affect how Python executes the code, but makes it easier for humans to read and maintain. Consistent formatting across a team's codebase helps prevent misunderstandings, reduces bugs, and shows professionalism. Even small details like spacing can make your programs look polished and approachable. Compound operators provide a shorthand way to update the value of a variable without rewriting the whole expression. For instance, instead of writing age equals age plus 1, you can use the addition assignment operator, written as age plus equals 1. Python updates the value in place, and the code becomes shorter and easier to read. The same principle applies with subtraction, multiplication, division, and modulo, giving you operators like minus equals, times equals, divide equals, and percent equals. This style is especially useful inside loops, where a variable's value is repeatedly updated. For example, a counter can be incremented or doubled with simple, compact syntax. Although these operators don't change what the program does, they make it easier to express common programming patterns clearly, helping you write code that's efficient, clean, and consistent with the style most Python programmers follow. Division in Python can be done in two ways, and it's important to understand the difference. Using a single slash performs true division and always produces a floating point result, even if the division comes out evenly. For example, 20 divided by 10 gives 2.0, not just 2. A second operator, double slash, is called floor division, and it rounds the result down to the nearest whole number. If both operands are integers, the result will be an integer, but if either operand is a float, the result will be a float rounded down. For instance, 5 divided by 10 with floor division gives 0, because the remainder is discarded. This distinction is essential when writing programs that need exact decimal values versus whole number results. Remember also that division by 0 is never allowed and will cause an error, so careful checks are important when using these operators. Alongside division, Python includes another arithmetic operator, the modulo symbol, written as a percent sign. Modulo evaluates the remainder left over after integer division. For example, 23 modulo 10 results in 3 because 23 equals 10 times 2 plus 3. The remainder is what modulo returns. This operator is especially useful for problems involving cycles, such as figuring out if a number is even or odd, repeating through a sequence, or breaking numbers into digits. In fact, modulo is commonly taught early in programming because it helps you understand how division interacts with remainders. Knowing when and how to use modulo gives you powerful control over loops, conditions, and numeric problems. It's a small operator with big practical value, especially when combined with other arithmetic expressions. One clever application of modulo is extracting digits from a number. By combining modulo with floor division, you can pull apart the ones, tens, hundreds, and higher digits of any integer. For instance, given the number 927, taking modulo 10 gives you the ones digit 7. Using floor division by 10 reduces the number to 92, and then applying modulo 10 again yields the tens digit 2. Repeating the process gives you the hundreds digit 9. This pattern works no matter how many digits the number has, making it a versatile tool for tasks like digit analysis, numerical puzzles, or data validation. What's powerful is how little code is needed to accomplish this. A simple sequence of division and modulo operations reveals the structure of the number in a way that's both logical and efficient. Modulo can also be used to extract larger portions of a number, such as prefixes. For example, given a 10-digit phone number stored as an integer, you might want to separate out the 3-digit prefix. By dividing the phone number by 10,000, you remove the last 4 digits and are left with the first 6. Applying modulo 1000 then isolates the last 3 of those 6 digits, which represent the prefix. The same principle applies to any number. Division by a power of 10 removes digits from the right, while modulo by a power of 10 keeps only the digits on the right. Together, they form a powerful pair for dissecting numbers. This technique demonstrates how mathematical reasoning can be directly translated into programming logic, making tasks like data parsing both straightforward and reliable. Python gives us 2 main ways to run code: the interactive interpreter and scripts. The interpreter lets you type and execute one line at a time, which is great for experimenting with syntax, testing quick ideas, or learning new concepts. However, for larger or more structured programs, using scripts is much more practical. A script is simply a file ending in .py that contains Python code. You save it, then run it through the interpreter by calling it from the command line with the command python scriptname.py. Scripts allow you to organize logic across multiple lines, reuse code by running it again, and share your program with others. Even a simple script that prints "Hello, Python" demonstrates the difference. When run, all of the file's instructions are executed in order, unlike the one-at-a-time style of the interpreter. As programs grow, they're often too large for a single file, and that's where modules come in. A module is just another Python file that can be imported into your program. By importing, you can use any variable, function, or class defined inside that module. Once imported, items are accessed using dot notation, which makes it clear where they came from. For example, if you define a constant like the speed of light inside a file called universe.py, another program can import universe, and then access that constant with universe.speedoflight. This separation allows for cleaner design, encourages reusability, and lets you share common functionality across multiple projects. Modular programming is one of the most effective ways to manage complexity as your Python projects scale. Splitting code into modules also mirrors the way professionals structure larger applications. For example, if you were building a simple Tetris-like game, you might create separate modules for handling user input, describing the different piece shapes, and managing the score. Each file would focus on just one aspect of the game, making it easier to test and maintain. Beyond custom modules, Python also provides a standard library full of pre-installed modules covering everything from math functions to file handling. As you learn more about functions and classes, the usefulness of modules becomes even clearer, since they help enforce logical boundaries in your code. In practice, modular design improves readability, reduces duplication, and gives you a more organized way to build complex systems. When working with modules, it's important to understand what happens when one is imported. By default, Python executes all of the code inside the module immediately. This can sometimes be unwanted if you only want to reuse certain parts of it. To handle this, Python uses a special built-in variable called name. If a file is being run directly, name equals main, and any code inside an if name equals main block will execute. But if the file is imported by another script, name takes the name of the module, and that block is skipped. This design allows the same file to act as both a standalone program and a reusable module. For instance, a file defining pet names might print details if run directly, but when imported into another program, only the variables are available. Python also includes built-in modules that extend its functionality, such as the math module. While basic operators like plus or times are fine for everyday math, sometimes you need more advanced calculations. The math module provides functions for square roots, powers, logarithms, trigonometry, and more. It also gives you access to constants like pi and e, which are essential in many scientific or engineering problems. To use it, you simply import math at the top of your file, then call its functions with dot notation, such as math.square root of 49. This modular approach helps Python stay lean while still giving you access to a wide array of specialized tools when you need them. The math module is a perfect example of how importing functionality keeps code efficient, organized, and powerful. Functions are one of the most important tools in Python, and the math module gives us many ready-made ones. A function is simply a reusable block of code that executes when called, often with one or more inputs called arguments. The function then returns a value that your program can use. For example, calling math.sqrt with the number 49 passes 49 as the argument, and the function returns 7.0 as the result. In this case, math.sqrt is the function call, 49 is the argument, and 7.0 is the return value. By wrapping complicated logic inside a simple name, functions make code more concise and easier to understand. Using module functions like these allows you to tap into tested, efficient implementations without having to reinvent the wheel, saving time and reducing errors in your programs. The math module includes a wide variety of functions grouped into categories, which makes it easier to know what to use for different problems. These categories include number and theoretic functions, which handle rounding, absolute values, and factorials. Power, exponential, and logarithmic functions for scientific and engineering calculations. Trigonometric functions for working with angles and periodic behavior. And finally, special functions and constants for advanced mathematics. Importantly, you only need to import the math module once at the top of your program, and then you can access all of these features. The Python documentation provides a complete listing, but learning the most common ones will cover most practical needs. This overview slide sets the stage for exploring these categories in detail with examples. Let's begin with number and theoretic functions. These are tools for handling basic mathematical properties of numbers. Functions like ceil and floor let you round numbers up or down to the nearest integer, while fabs gives the absolute value of a floating point number. Factorial, which multiplies an integer by all the positive integers below it, is another example. There are also functions like fmod, which calculates the remainder in floating point division, and fsum, which performs an accurate sum over lists or ranges of numbers. These functions may seem simple, but they are widely used in scientific, financial, and statistical applications. For instance, rounding values, computing factorials, or summing a large dataset with precision all require these capabilities. The math module provides them efficiently and consistently, freeing you from writing manual implementations. Power, exponential, and logarithmic functions extend Python's basic arithmetic to cover essential operations for science, finance, and computing. The sqrt function calculates square roots, while pow raises a number to any power, much like using the double asterisk operator but with added clarity. The exp function computes e raised to a given power, a cornerstone of exponential growth calculations, and the log function provides natural logarithms by default, though you can specify other bases like 10. These functions are critical in areas like physics, economics, and data analysis. For example, exponential functions model population growth, and logarithms are used in measuring sound intensity or financial returns. With the math module, you can perform these advanced calculations in just one line of code, which makes your programs more powerful and expressive. Trigonometric functions round out the math module's key offerings by letting you work with angles and periodic behavior. Functions like sine, cosine, and tangent handle trigonometric ratios, while their inverse counterparts, arcsine, arccosine, and arctangent, return angles from ratios. Arctangent, too, is especially useful because it calculates the angle from x and y coordinates, handling quadrants correctly. Functions for converting between degrees and radians simplify working with different angle systems, while hypot computes the length of a vector from the origin, a direct application of the Pythagorean theorem. Hyperbolic functions like hyperbolic cosine and hyperbolic sine are also included for more specialized use. These trigonometric tools are invaluable in graphics, engineering, navigation, and even game design, where precise angle calculations drive movement and positioning. With the Math module, you gain direct access to all these capabilities in a standardized and efficient way. Beyond arithmetic and trigonometry, the Math module also provides special functions and constants that are widely used in advanced mathematics and science. The gamma function generalizes factorials to non-integer values, while ERF, the error function, appears in probability and statistics. Constants like pi and e are built in, eliminating the need to define them manually. Pi, approximately 3.14159, is fundamental in geometry and trigonometry, while e, about 2.71828, underpins exponential growth and natural logarithms. Having these constants directly available not only saves time, but also ensures accuracy across your programs. For example, whether you're calculating the area of a circle or modeling exponential decay, you can rely on math.pi and math.e to provide precise, consistent values. These functions and constants expand Python's capabilities, making it suitable for everything from basic coursework to professional scientific computation. Many programs also need random numbers, whether for entertainment, security, or simulation. Games use them to roll dice or shuffle cards, while websites might generate random passwords. Python's random module provides these features. The random function specifically returns a floating point value between 0, inclusive, and 1, exclusive. Each time you call it, the function generates a new value in that range, making it useful for probability and simulation problems. To use it, you must first import the random module, and then you can generate as many random numbers as needed. The values change with each run of the program, ensuring unpredictability. This randomness is pseudorandom, meaning it's generated by an algorithm but appears random enough for most applications. This makes random.random a powerful tool whenever your code requires variability or unpredictability. Sometimes, you need random integers rather than floating point values, and that's where randrange comes in. When given a single integer argument, randrange produces a random integer between 0 and that number minus 1. For example, randrange with an argument of 10 will return values from 0 through 9, giving you 10 possible outcomes. This is especially useful when simulating dice rolls, picking random indices from a list, or working with ranges of discrete numbers. Because the upper bound is exclusive, you can easily control the size of the output range. Calling randrange repeatedly will produce different values within the specified range, ensuring unpredictability. This function adds flexibility to the random module and is a building block for many more advanced randomization tasks, like sampling or generating random sequences. Often, programmers need random numbers within a custom range that doesn't start at 0. In this case, Python provides both randint and randrange with 2 arguments. Randint generates a random integer between the minimum and maximum values inclusively, while randrange generates an integer starting at the minimum but excluding the stop value. For example, randint between 12 and 20 will produce any number from 12 through 20, while randrange with the same arguments only goes up to 19. These functions are especially useful in real-world applications, such as simulating dice that return values from 1 to 6 or generating random years, ages, or other bounded data. By offering both inclusive and exclusive ranges, Python gives programmers precise control over random integer generation, which is critical in applications requiring fairness, accuracy, or predictable limits. Random numbers can also be used to simulate real-world scenarios, as shown in the example of moving a student randomly within a lecture hall. Imagine a classroom with 20 rows and 30 seats per row. The program first chooses a random seat from the left side, defined as columns 1 through 15, and then assigns a new random seat on the right side, defined as columns 16 through 30. This uses Randint with appropriate ranges for both rows and columns. The output shows the original and new positions, demonstrating how random integers can drive practical simulations. Such techniques are common in scheduling, seating assignments, randomized experiments, and even simple games. By combining basic programming with random number generation, you can build tools that mimic real-world uncertainty and create dynamic outcomes, reinforcing how versatile and valuable Python's random module is. The random numbers generated in Python are called pseudorandom because they are not truly random, but are generated by an algorithm that produces values that appear random. Internally, each number is calculated from the previous one, and the very first number is determined by a starting value called a seed. By default, Python uses the current system time as the seed, which means each run of the program produces a different sequence. However, you can explicitly set the seed with random.seed, and when you do, the sequence of numbers becomes reproducible. This feature is extremely useful for testing and debugging because it allows you to recreate the same results consistently. For example, games like Pac-Man depend on repeatable randomness for fair play and consistent behavior. Pseudorandom numbers strike a balance between unpredictability and reproducibility, which makes them both practical and powerful. Python also supports text through Unicode, which allows it to handle characters from nearly every written language in the world. Each character in Unicode is represented by a unique numeric code point. For instance, the capital letter G has the code .71. Unicode covers over 1 million characters, including Latin alphabets, Greek, Cyrillic mathematical symbols, and even emojis. This wide range ensures Python can work with text in global applications, whether you are processing English, Chinese, or even symbols like musical notes. The ORD function lets you convert a character into its numeric code point, while CHR performs the reverse, converting a code point back into a character. With Unicode, Python provides a consistent way to handle text, making programs adaptable across languages, regions, and specialized contexts without requiring special adjustments. Not all characters are visible. Some are special control characters represented with escape sequences. An escape sequence is a 2-character combination that begins with a backslash. For example, the newline character, which indicates the end of a line, is written as \n, while a tab character is written as \t. Escape sequences allow programmers to include special formatting within text strings that would otherwise be invisible. For example, a newline moves output to the next line, a tab adds spacing, and \quote allows quotation marks to appear inside a string. Python reads the backslash and interprets the next symbol to determine the meaning. These sequences are essential for formatting output neatly and for working with text data that requires invisible or structural characters, like file paths or structured text files. Sometimes, escape sequences can get in the way, which is why Python supports raw strings. A raw string ignores escape sequences, treating backslashes as literal characters. You create one by adding an R before the string, like R. This is a raw string. In this case, Sequences like \n are not treated as newlines, but are displayed as plain text. This is especially useful for working with file paths on Windows or regular expressions, where backslashes are common. In addition, Python provides functions to move between text and its encoded numeric representation. The ORD function takes a single character and returns its Unicode code point, while CHR takes an integer code point and returns the corresponding character. Together, these features give you flexibility in handling text. You can display it normally, ignore formatting sequences when needed, or work directly with its encoded values. Finally, let's step back and consider Python-style guidelines as a whole. Different teams and projects may have their own rules, but the key idea is consistency. Code that follows a consistent style is easier to read, easier to maintain, and more professional. In Python, many of these guidelines are inspired by PEP 8, the community's standard style guide. Following these conventions doesn't change how the program runs, but has a big impact on readability and collaboration. The examples we've been looking at include guidelines for whitespace, naming conventions, and how to format strings and operators. By adopting a standard style early in your programming journey, you'll build habits that will make your code clear to others and easier to extend later. Think of it as good communication, not just with the computer, but with other people who may read or work on your code. Whitespace plays a critical role in making Python code readable, and style guidelines emphasize keeping it consistent. Each statement should appear on its own line rather than combining multiple statements with semicolons, which makes code harder to follow. Blank lines should be used sparingly, only to separate sections of logic, not between every line. Operators like plus and minus should have a single space around them for clarity, and substatements within control structures, such as if statements should be indented exactly 4 spaces. Tabs should be avoided because they can display inconsistently across different editors. Following these practices makes code easier to scan and reduces errors caused by misreading crowded or poorly spaced expressions. Clean, consistent whitespace is a simple but powerful way to improve the quality of your programs, helping you and others read and maintain them more effectively. Naming conventions are another pillar of Python's style guide. Variables and functions should be written in snake case, meaning all lowercase letters with words separated by underscores. This makes names clear and easy to distinguish from constants, which should be written in uppercase with underscores, like maximum weight. Class names follow a different convention, using camel case where each word begins with a capital letter. Names should also be descriptive, using at least 2 words when possible to avoid confusion. Single letters are discouraged, except for loop counters or mathematical expressions. For example, numitems is far clearer than simply num or n. Similarly, user key is preferable to USR key or K. By following these conventions, you make it obvious what each variable represents and create code that is self-documenting, reducing the need for extra comments while improving readability for everyone who works with it. In addition to naming and whitespace, there are some miscellaneous conventions that further improve readability. For consistency, double quotes are generally preferred for string literals, although Python accepts both single and double. Keeping your lines under 100 characters makes the code easier to view across different editors and screen sizes. If a line of code is too long, break it into smaller parts rather than forcing it all onto one line. This improves readability and helps prevent mistakes. For example, long messages or complex expressions can be split across multiple lines while still being clear. The goal of these conventions is not strict rules for their own sake, but practices that make code approachable and easy to maintain. Following them ensures your programs are not only functional, but also clean, professional, and pleasant for others to read. To wrap up, Let's review the key ideas from this lecture. Variables bind names to values, and reassigning them updates that binding. Identifiers must follow rules and should be descriptive, while style guidelines keep code readable and consistent. Everything in Python is an object, carrying a value, a type, and an identity, and knowing whether objects are mutable or immutable helps you predict their behavior. Arithmetic expressions, precedents, and operators like division and modulo form the foundation for calculations. Python's math and random modules extend these capabilities with advanced functions and randomness for simulations. Strings are represented in Unicode, with escape sequences, raw strings, and encoding functions like ORD and CHR enabling flexible text handling. With these tools, you're now prepared to write programs that are not only correct, but also clear, idiomatic, and maintainable skills that will serve you well as you tackle more advanced Python programming challenges. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.